Hello everyone! With this video, we are now starting a new series regarding complex numbers. In this series, we will first see some basics and definitions of complex numbers, and in the second course, we will look for how to solve equations and complex problems concerning complex numbers. And lastly, we will see in electrical engineering and its applications, how can we use complex numbers and for what sub-problems, for what topics we have to use complex numbers, and how do we deal with complex numbers within the scope of electrical engineering. For this particular video, for our first video, we will be revisiting the definition of complex numbers. We will see some algebraic features of complex numbers, and we will see some basic equations and simple problem-solving techniques using multiplication, division, addition, and subtraction using complex numbers. The idea behind the complex numbers is built on the square root of -1. So how this is possible is quite complicated, as the number's name suggests. So every time we square a negative number, we got a positive number. And every time we square a positive number, of course, we again get a positive number. And if we take the negative of a square rooted number, it will be a negative square root number, but it won't be square root of a negative number. So this is completely a different topic. As we said, square of -1 equals to 1, just as square of 1. And square of -2 is 4, and square of -3 is 9, and so on. And the question arises, is there a number that, when multiplied by itself, gives us a negative number? The answer is both yes and no, and depends on your set of numbers. In the very large and inclusive set of complex numbers, our answer is yes, and this is the number I. I stands for the imaginary number, and the first letter of the imaginary is I, so this is why we call this number I. But in some engineering applications, especially in some equations, some vectorial operations, we use I for different quantities. For example, in circuit theory, we use I for current, the amperage of the given components or the circuit itself. So in order not to confuse it with the current I, sometimes we use J instead of the complex I. Since it is easy to confuse it, especially when dealing with complex numbers, also in the circuit theory, we should pay some extra attention. And the formal definition of this I, as we use in maths and non-circuit or non-physics related content, this formal definition is quite basic. It is square root of -1. So we cannot obtain this by using other relations and identities defined in whole numbers or real numbers, but we should imagine that this number exists and continue our operations. We are already told that squaring a negative number always gives us a positive number. But this is not the case for I. For this very specific case, we can get a negative number because I equals to square root of -1, and if we take the square of I, then we will get rid of the square root and the remaining result will be -1. And this is the key point of using I in equations and algebra. Here in this video, we will have a lot of examples to make it more clear and understandable. And we will see how do we use I equals to square root of -1 in simple relations and equations. Let's look at the left part. Square root of -16 can be written as square root of 16 times square root of -1. So we can somehow factor this number. And as we already know, square root of 16 is 4 and square root of -1 is, as defined right now, I. So the result is 4i. So square root of -16 is equal to 4i. On the right side, we have square root of -81, and in the same way, we can write this as square root of 91, which is 9, times square root of -1, which is I. So the result would be 9i. So 9i is exactly the same as square root of -81. Another example for square root of -45 could be square root of 45 times square root of -1. Square root of 45 is not resulting a whole number, but we will get eventually square root of 9 times 5 times square root -1, and this will give 3 times square root of 5 times square root of -1, and this will be 3i times square root of 5. And similarly, square root of -200 would be square root of 200 times square root of -1, which will give us square root of 100 times 2 times square root of -1, and which will give us, when we replace square root of -1 with I, which will give us 10 times square root of 2 times I. However, this is not the whole story. There is something very interesting with I. So let's look at the powers of I. And I to the power of 1, the first power, is obviously I itself. So it's square root of -1 again. This is very expected. And I squared is -1, as I already explained before. And I to the power of 3, I cube, is I squared times I. So this will make -1 times I, and it will be -I. And here is the magic. I to the power of 4 equals to exactly 1. So there is an interesting pattern here, because why this is 1? Because I to the 4 means that I square times I square, and this means as -1 times -1, and when we multiply two minuses, we will get the positive result, and it will be 1. So there is a cyclic pattern, because if you calculate I to the power of 5, then you will multiply I with I to the power of 4. Then you will multiply I with 1, and you will get the 1 again. So the pattern turns to the initial position and will start again from I to the 1. This pattern should better be memorized. Powers of I builds a cyclic pattern that repeats itself in every fourth power. So the pattern is clear, but how can we deal with larger powers of I, like I to the 36th, I to the 39th, or I to the 100th? It's quite easy as well. We should divide the power exponent by 4. If there is no remainder, the answer is 1, just as I to the 4th. This means that we can divide this exponent number by 4 with no remainder. If remainder is 1, then answer is 1. And if remainder is 2, the answer is -1. And if remainder of 3, the answer is -I. Using this technique, we can find I to the 23rd. We should divide the exponent 23 by 4, and the remainder would be 3. So we will get -I. And I to the 2006 would be -1 for the same reason, because the closest number that we can divide to 4 is 2004, and the remainder would be 2. So it should be I squared, which is -1. And I to the 37th would be I for the same obvious reason, because remainder is 1 only. And I to the 828 would be 1, because we can divide 828 by 4 with no remainder. Complex number system is a very large set of numbers. It includes natural numbers from 1 to the infinite, and also whole numbers. Of course, 0 is another complex number, because you can always assume that it is 0 times I or 0 plus I. We also include integers, and as we already have -I, so negative numbers are also a part of the complex number system. We also have rationals. I can be divided. We also have irrationals, pi, e, and we also include real numbers, which is already a large set itself, but the complex number system is the largest so far. Here, what is included to the complex number system that is excluded from the real numbers are the imaginary numbers. Numbers like I, 2i, -5i, -3, -7i, etc. are imaginary numbers included in the complex number system, but excluded from the real number system. Let's continue expressing the numbers in terms of I to make a better understanding. Square root of -5 would be square root of -1 times 5, and if we separate these numbers, we'll get I times square root of 5. And minus square root of -7 would be minus square root of -1 times 7, and which will eventually be minus I times square root of 7. And square root of -99 would be, of course, square root of -1 times 99, and this would be I times square root of 9 times 11 in the square root. And we can put 9 here out of the square root function, and we will get 3 times I times square root 11. You can also try square root of -7 minus square root of -36 and square root of -160 yourself. We have the answers here. You can stop the video and solve how do we reach these answers. We can, of course, multiply imaginary numbers with real numbers and again with imaginary numbers. So it's always possible to multiply an imaginary number within the complex number system with an imaginary number or a real number or any other number inside the system. To multiply the imaginary numbers or an imaginary number by a real number, it is important to first express the imaginary numbers in terms of I. So it could be much harder if we leave the numbers here square root of -7. This will be very hard and could be wrong at the base case. But if we convert it to the I representation of that complex number, then it will be much easier to proceed with the multiplication operation. Here, when we convert the complex number to the I representation form, then I should be treated like a variable, like we use x or y in some equations. So I should be treated like a variable, and then it should be changed to the first power if it is not represented as the first power. Let's look at the left example. Here we have -I times parentheses 3 plus I. So here we distribute I inside the parentheses and we get -3I minus I square. Here I square is not to the first power, so we have to resolve it. We already know what does it mean. And we get -3I minus -1, and we will eventually get 1 minus 3I. In the second example, we have 2 plus 3I times -6 minus 2I. And we can make the multiplication inside the parentheses, and we will get -12 minus 4I minus 18I minus 6I squared. Here 4I and 18I are all to the first power, and we can just subtract or add them just like any variable here, and we have to resolve I square, and we will get -12 minus 22I plus 6 as we multiply -6 with -1. And eventually we will get -6 minus 22I as the simplified result. Multiplication with real numbers is very straightforward. 47I times 2 is 94I. And 2I times square root -5 requires more attention because we have to convert square root -5 to the I formation, and we will get 2I times square root -1 times 5, and here we get I. So it will be 2I times I square root 5, and we can resolve the I square here, and we will get -2 times square root 5. In the last example in this page, we get square root -3 times square root -7. Here, first thing to do is to convert to the I formation here, and we will get -I times square root 3 times I times square root 7. And we will eventually get from this equation -I square, which is already -1, times square root 21, and which is just regular positive square root 21. What we call a complex number is usually a number in the form of a plus b times I. Here, b times I is the imaginary part because it contains the I, the imaginary number itself. And a here is the real part. A and b here are real numbers and can be even 0. So 5I, for an example, fits in this form as well, because if we take the example of 5I, it could be written as 0 plus 5i. So for the 5i case, a is 0 and b is 5. And we have the I at the end. So 5i could be written as 0 plus 5i. And it's the same for all numbers. And this is the reason why real numbers are also complex numbers, because 25 can be written as 25 plus 0i, where a is 25 and b is 0. So we will lose the effect of I here, and 25 would be a complex number without an imaginary unit. Let's look at addition and subtraction. When adding complex numbers, we add the real parts together and add the imaginary parts together. So we do not add real parts and imaginary parts. We do not mix and match. We only add real parts to real parts and imaginary parts to imaginary parts. So if we add 3 plus 5i to 8 plus 11i, we will only add 3 to 8 and 7i to 11i, because 3 and 8 are the real part, which represent a in the generic form, and 7i and 11i would be bi in the generic form. So this will be the result, 11 plus 18i. So we cannot proceed from here. This is the final formation of this adding operation here. And when subtracting complex numbers, be sure to distribute the subtraction sign and then add parts like the addition operation. Just so when you distribute the minus sign inside the parenthesis, then you will get the addition with no special difference. So 5 plus 10i minus 15 minus 2i would be just 5 plus 10i with no change here, minus 15 plus 2i when we distribute the outer minus inside the parenthesis on the right hand. And if we make the addition here, we will get minus 10 plus 12i. Seven I plus 9i would be very straightforward, very easy. It's just 16i. And in another example, we have minus 5 plus 6i plus 2 minus 11i here. Minus 5 and 2 are the real parts, and 6 and 11 are in the imaginary part. So we will add real parts to real parts and imaginary parts to imaginary parts, and we will get minus 3 minus 5i. And the last example here, we have 2 plus 3i minus 4 plus 2i, and this translates as, if you distribute the minus sign inside the right parenthesis, we get 2 plus 3i minus 4 minus 2i, which translates as minus 2 plus I only. Here we have a little bit more complicated examples, but not too much. And the first one, the question asks I times square root 3 squared. And we can distribute the power square inside because there is a multiplication inside the parentheses. And it will become I squared times square root 3 squared. And I squared is, we already know that minus 1. And square root 3 squared is only 3. So this would be minus 1 times 3, and we get minus 3 as a result. And the second one, we have a polynomial. It is 3x squared plus 10 equals to minus 26. Here we can subtract 10 from each side, and we will get 3x squared equals to minus 36. So far we do not have I, but we will have soon. From here we can divide both hands with 3, and we will get x squared equals to minus 12, and we can square root both sides, and which will yield square root of x squared equals to square root of minus 12. Here we get the I. X equals to plus or minus I square root 12. Here we have the sign plus or minus because we cannot know if it is positive or negative due to the nature of square operation. And from here we get x equals to plus or minus 2 times I times square root 3. Division is not straightforward like addition or subtraction, but not hard either. To divide complex numbers, we multiply the numerator and denominator by the complex conjugate of the complex number in the denominator of the fraction. And you will understand better when we see the examples. Let's divide 7 plus 2i to 3 minus 5i. Here, in order to make this division, we have to find the complex conjugate of the denominator part, and since it is 3 minus 5i, the conjugate would be 3 plus 5i, and in this case we have to multiply both hands of the division with 3 plus 5i. This would not change the result, but will help us solve the problem. If we make the multiplication, we will get a polynomial representation as I was just like a variable. And if you multiply 7 plus 2i with 3 plus 5i, we will get 21 plus 35i plus 6i plus 10i squared. And with the denominator, we will get 9 plus 15i minus 15i minus 25i squared. And here we already know what is I squared. It is minus 1. So we will get 21 plus 41i minus 10 over 9 plus 25. And here we will get 11 plus 41i over 34. So I guess you have an understanding of why we are doing that multiplication for both hands of the division. It's because we want to get rid of the I in the denominator part and would like to have it on the upper side on the division. In this case, we can just remove the I or make it disappear from the denominator, and we'll have the resulting complex number in the generic form of a plus bi. From here, this result does not look like a plus bi, but it can easily be converted to I plus bi if we make the division 11 over 34 plus 41 over 34i. So this will be a plus bi, where 11 over 34 is a and 41 over 34 is b. Let's look at another example. 3 plus 11i over minus 1 minus 2i. Here the complex conjugate of the denominator part is minus 1 plus 2i. So we will multiply both sides with minus 1 plus 2i. And we will get minus 3 plus 6i minus 11i plus 22i squared for the denominator, and 1 minus 2i plus 2i minus 4i squared for the denominator part. In the next step, we can replace I squared to minus 1 on both sides, and we will get minus 3 minus 5i minus 22 over 5. And this will give us minus 25 minus 5i over 5 and minus 25 over 5 minus 5i over 5, and which is simply minus 5 minus I. So the result of this complex number division is indeed a simpler one. For today, we have learned the very basics and fundamental features of the complex numbers, and especially the imaginary unit I, and how to interpret I, how to use it in algebraic equations, the powers of I and the magical pattern of powers of I, and 4 fundamental operations, including multiplication, addition, subtraction, and division using complex numbers. For the next course, we will be focusing on much more complex equations and polynomials, as well as some advanced problem-solving techniques. Thank you.